Welcome back, AP Physics, Electricity, and Magnetism students. In this video, I will show you how to derive the capacitor charging and discharging equations that I mentioned or showed you in the previous video. So here's the basic circuit. We're going to start first with the charging equations, the basic circuit. We've got a voltage source, a battery, M, a switch, an uncharged capacitor, and a resistor, R. So the switch will flip down and initiate the charging. We want to know the charge is a function of time, and the current is a function of time. As I mentioned in the last video, there are 4 basic steps to solving these differential equations problems. The first step, you have to make a differential equation using Kirchhoff's loop rule. As I mentioned in the other video, in mechanics we use Newton's laws to make a differential equation. But the loop rule, what you basically do is, as I mentioned before in the other video, you pretend you're a little ant maybe that starts at point A and walks around the circuit in the direction of the current with a voltmeter, a little tiny voltmeter, tallying up all the voltages as you walk around in the direction of the current. And when you do that and complete the loop, you'll get 0. So the first thing that happens, the ant will encounter the battery. Walk from the negative terminal to the positive terminal. So that means the ant is going up in voltage, plus M of the battery. The ant keeps walking, encounters the capacitor. Now while the capacitor is charging, this side's going to be positive, this side's going to be negative because of the way the current's flowing. So the ant's going to walk from the positive plate of the capacitor over to the negative one. So it's going to go down minus voltage. How much voltage? Q over C. Again, that comes from C equals Q over V, solving for V, the basic capacitor equation. The ant keeps walking, encounters the resistor R, walks downstream through the resistor, downhill, right? If you're going with a river down a mountain, you're going downhill, so you go down voltage minus IR, and then it's completed the loop, so the voltage around adds up to 0 over here. Still not a differential equation because we don't have a derivative in it. So we replace I with the definition of what I is, the derivative of charge with respect to time on the capacitor plates. Okay. Now it's a differential equation. Okay. I guess I've already begun separating the variables, but that's step 2. We make a differential equation, step 1. Step 2, we separate the variables. That means we've got to get all Q variables on one side, all time variables on the other. So what I did is I moved the derivative R dq dt to this side, okay, and then with the remaining 2 terms right here, M minus Q over C, I found a common denominator by multiplying this by C over C, and so I have C minus M, C M minus Q in the top all over C. And then to separate the variables, I got to get all the Q's over to this side and all the times to the other. So what I did is I divided by this entire numerator here. So see, we have dq over c m minus q. This whole numerator ends up on this side, divided over. The r and the dt, I moved over to the other side. So I divided both sides by r, so we have rc now together in the denominator, and the dt over to the other side. Okay, so there is... So the variables are separated, all Q's, all times. Third step, we integrate both sides. So I'm integrating, the charge on the capacitor began at 0, and then it goes up to some final charge. And the time, our stopwatch in the experiment begins at 0 and ends at T final. This integral just is like du over u, with a minus sign, or I should say negative du over u if you did a u substitution. That integrates to the natural log of u. So, and then with a minus sign there. This side, real easy, dt just integrates to t. So then the fourth step, separate the variables, make a differential equation, separate the variables, integrate both sides, solve for q final. That's what we want. Okay, so we plug in our limits, q final here, and then 0 here. Right? So there are the limits plugged into the log function. I also moved the minus to this side, by the way. And then I plug in t final and 0 here. I could combine these two logs into one. As with a subtraction, we make a division inside the natural log function. Now, what we have to do is solve for q, so that means we got to get rid of the natural log. We could put both sides of the equation into the exponential function. That'll eliminate the log. So that's what I did here. And that just leaves me what's inside the log, and then e to the minus t on RC. Again, I'm just solving for q. I move the c times mth to this side, then I move the c times mth, I multiply it here, and then I subtract this over to this side, and then I multiply both sides by minus 1. That makes this first, and this exponential second, and then I factor out the c times mth. There is the charging equation. Again, a reminder that RC can be replaced by tau. So tau is equal to RC. Okay, so we could rewrite that like that. Now, to find the current as a function of time, I basically have to take the derivative of this with respect to time. So easier if I distribute this c mth in through the parentheses, and then when I take the derivative of that, the derivative of this is 0 because it's a constant, and then the derivative of this is the derivative of the exponential is just the exponential, but then I have to multiply by the derivative of what's inside the exponential because of the chain rule. So that gives me a negative 1 over RC here. C's go away, and there's the current as a function of time. Okay? So I could plot those two, and the 1 minus exponential rises to c times mth, and this one decays down to 0. So there's the derivation. Again, 4 steps. Set up the differential equation with Kirchhoff's loop rule, separate the variables, integrate both sides, and then plug in the limits and solve. Next, I'm going to derive the formulas for discharging a capacitor. Okay, so I go through the same exact process, only now the circuit looks like this. There's no more battery, there's a charged capacitor waiting to be discharged, and a resistor, and a switch, that's it. When this switch closes, flips down, the capacitor will begin discharging through the resistor. And so I want to find Q as a function of time. Once again, the 4 steps. The first one, we make a differential equation using Kirchhoff's loop rule. So again, we pretend we're a little ant with a little voltmeter. We begin at some point in the circuit and we walk around and tally the voltage in that circuit. First thing the ant will encounter is the capacitor. Walking from the negative plate of the capacitor to the positive, it's going to go up volts. Plus, what's the voltage of a capacitor? From C equals Q over V, you could solve for voltage and get Q over C. The ant keeps walking, encounters the resistor, walks through it in the direction of the current. It's like going downhill with a river, so the voltage is minus. How much voltage? Minus IR. Okay? Still not a differential equation, so we got to eliminate I with a derivative of charge. But here's the thing. Notice there's a little extra minus sign there. Why is that minus sign there? Well, because technically the derivative of charge with respect to time is negative because the capacitor is decreasing its charge with respect to time. So if I didn't have that minus there, I would actually be plugging in a negative current. So I put a minus. So what I really have is a minus minus, which is a positive current. Without that minus there, you don't get the right answer for the charge as a function of time. All right, so I made a differential equation with Kirchhoff's loop rule. The second thing I got to do is separate the variables. Get all the Q's on one side, all the time variables on the other side. The way to do that is divide both sides by Q, so I have dQ over Q, and then move the R and the dt over to this side. I divide negative R, so the 1 over C becomes negative 1 over RC. And then the dt is by itself. Integrating both sides, the limits are the charge starts at the original charge of the capacitor, Q0, to some final charge as it's decaying down. The timer in our experiment began at 0 and it goes to T final. The left side, just a simple natural log of q over those limits. The right side, dt, just integrates to t, from 0 to t final. If we plug in our limits, the fourth step is plug in the limits and solve for q. So we plug in q final, log of q final, and then plug in q0. And then plug in t final and 0, our two limits. We could combine these logs into one. Okay, with the subtraction, you put this term in the denominator inside the log. Moving on, we can get rid of the log by taking the or putting both sides of the equation into the exponential function. So the log goes away, and we just left with q final over q0, and then this is inside the exponential e to the minus t on RC. Move the q0 to the other side, and there you are. You get the final charge decaying with a negative exponential decay. Now the current is defined as normally dq dt, but remember what I said, I had to have an extra minus sign in here because the charge is actually decreasing on the capacitor plate. So if I want the current to come out positive, I got to put a minus, so then I'll have a minus positive current. So I plug in the charge that I just got in for q, take the derivative of that. The derivative of the exponential is just the exponential. But then I've got to apply the chain rule times the derivative of what's inside here, which is the derivative of t is just 1. So I have negative 1 over RC. And here's the current as a function of time. So the charge begins at q0 and decays down. And the current starts at q0 over RC, decays down. Remember the time constant unit, RC, is actually in seconds, so we have coulombs per second here. So that's it, okay? 4 steps: set up the differential equation, separate the variables, integrate both sides, plug in the limits, and solve. All right, so glad you joined me for this second supplementary video, and I'll see you in the next review video.